moved as a postdoc fellow with Professor J.W. Perry in Department of Chemistry at the University of Arizona. In 2002, he became as assistant professor in the Department of Material Science and Engineering at MIT. There he became associate professor with tenure in 2009. In 2010, he moved as a full professor to EPFL, where he holds the Consulum chair. Stellacci has published more than 130 papers and has more than 15 patent applications. He has won numerous awards, among them the Technology Review TR35 Top Innovator Award, Innovator Under 35, the popular Science Magazine Brillianton Award, and the EMRS EU40 Award. He is a fellow of the Royal Society of Chemistry, of the Global Young Academy, and of the European Academy of Sciences. With these introductory words, I welcome Professor Stellacci for his talk. You have 40 minutes, sir. Thank you.
Okay, thank you, everybody. The title of my talk is a process for recycling that I have invented that's called NaCRe, which stands for Nature-Inspired Circular Recycling. And I'm going to tell you today about that. But the real title of my talk is that plastic is a very difficult problem. And even broader than that, what I'm going to tell you today about is that in the world of materials, sustainability is a huge issue. And the reason for that, as I will try to explain, is because on Earth, we are 8 billion. And in 20 years, we're going to be 10 billion. And at the heart of a problem is this huge number. But we're going to talk about plastic. So please allow me to give you a very short history background. Plastic material have been used for thousands of years on Earth. In fact, the Aztec played a game with ball and a stadium already 2,000 years before Christ. And that ball was made of caoutchouc, came from trees. This use of caoutchouc was diffused in India also. But it's only around medieval time, both in India, then in Europe, that people start actually molding plastic materials from nature to actually make products. Some of them we still have to date. They're not considered noble as noble metals, but actually they were the start of a lot of things. But then, really, a lot of things happened in a very short period of time. In 1823, Macintosh uses rubber to actually coat cotton and makes the first waterproof material, clothing, which is a huge conquer for a country like England, where they were using ships to go throughout the world. A simple thing makes their sailors fall less ill and allows their conquer of the world. Whether that was good or not, it's all a debate. But that was enabled by Macintosh. In 1839, Goodyear makes the first vulcanized plastic. And with that, we have tires. And with that, we have a first bicycle. Okay? Just soon after. But if Goodyear doesn't make the tires, try riding the original bikes, which were 3 meters high, on a wooden tire, which at the first stone, you're going to fall 3 meters down. In 1885, Kodak patents the first film machine. We are first able to make films. And photography comes soon after, thanks to chemistry. But if Kodak doesn't make the film, there is no photography. In 1907, Baekeland discovered the first synthetic resin. So all the way here, we've only used nature to make plastic. It's only in 1907 that Baekel makes bakelite, which is the first synthetic one. And the year after, Brandenburger invents cellophane. Cellophane, 1908. Huh? In 1909, and this number, casein, which is a cheese protein is used to make a plastic. So it's from 1909, we know how to make plastic from food waste. All the way here, nobody knew what plastic was. And now I'm going to tell you a story. In 1920, Staudinger, who's a chemist, hired at ETH Zurich in Switzerland. He's a German guy. He says that plastics are material made of polymers, and polymers are long macromolecules made of a repetition of units. This you've studied in chemistry. But what you don't know is that immediately Staudinger receives a letter from the German Chemical Society. He's expelled because his polymer theory violates entropy, which is interesting because entropy is a concept that had only been postulated 30 years before in Zurich. And the guy that had invented it was still in Zurich and no problem with Staudinger thing, but the German society expels it. Berzelius says that polymers are macromolecules made by a repetition of molecules not covalently linked. Okay? Soon after, Staudinger wins. We think macromolecules are the polymers. Berzelius is forgotten. Up to 10, 20 years ago, where macromolecular polymers were rediscovered, and Berzelius wasn't wrong either. You see, sometimes in science we have debate, and we're all right. You're just looking at problems in different ways. But the other key numbers that are for plastic is 1932, injection molding is patent. 1938, we make the first nylon 6 fiber, okay? And socks are invented. Plastics becomes a cheap material to make everything. Look around yourself. The chairs you're sitting on, everything, the glasses you have, they're all made of plastic. Plastic is the cheap material that has enabled our society. Without it, making things is too expensive, and there's no 20th century. Let's just be clear about it. Now, by the way, in all of this, there's only one limitation of plastic, that is that they're insulator. They're not good for electronics. But in year 2000, McDermott and others find that actually plastic can be conductive. And right now, if you have a Samsung cell phone, you're using conductive plastics. So plastic does everything. And again, these are polymers, long repeating units of the same molecule. It doesn't need to be the same molecule. It can be a mixture of molecules, then we call it copolymer. And it may be that actually the order of repetition of a monomer matters. This is what is done in nature. In this case, we call the polymer a sequence-defined polymers. And we know two classes of sequence-defined polymers that are very important. Nucleic acid, so DNA and RNA, and proteins. These are polymers, they're plastics. Life is based on them, and what is special about them, they are repeating, and the repeats encodes information. What information? Every 3 bases in DNA encode one amino acid. So DNA encodes for the synthesis of proteins, which are made of a repeat of amino acids. And those proteins allow life, okay? But let's go back now to what was discovered in 1907, synthetic polymers. They are at the heart of our society. They are the cheap material that has allowed our society, but they are not meant to degrade. Because degradation typically is a phenomenon that happens in solution. You know, nature degrades things by aqueous solution enzymatic processes. That's the way it works. But unfortunately, for the Staudinger saga, a polymer, you know, what is the solution? A polymer contains a lot of entropy in the chain. When we dissolve things, we dissolve them by an entropic driving force. That doesn't work for polymers because they already have the entropy. They don't go in solution. They don't go in solution, they don't degrade. So what happens to all of the plastic materials on Earth? Well, what happens to all of these plastic materials is that it gets burned and it produces CO2. That, believe it or not, is best case scenario. Because the other thing, it gets in the environment and it stays there, and I'll tell you later even more about it, or it gets into animals, into plants, in beings, living beings, plants or animals, and it gets in the food chain of everything. There is an estimate, each one of us eats 50 milligrams of plastic a week. That's how much we eat. That's what happens there. Now, to understand this, how big is the problem, we need to understand there's a lot of us on Earth, and we use a lot of plastic. How much plastic? Each one of us, averaged, is responsible for approximately 50 kilos of plastic every year of our life. So, if we take a normal life expectancy of 80 years, which is where the world is going, more or less, that's 4 tons of plastic in your lifetime. Each one of us is responsible for 4 tons of plastic. And
4,000 kg.
yes. And where does this plastic end up? You see, only 9% of plastic is recycled. The rest ends up landfilled, 174 million tons a year, happens incinerated, 67 million tons a year, or it's released into the environment, 79 million tons a year. Million tons a year. These are the size of a number every year. Believe it or not, this is the best thing that can happen when plastic gets burned. Even though it produces CO2, and in some countries it's at least used for some energy generation, okay? Because these two, what happens with these two? What happens with these two is that when it gets released into the environment, sooner or later it reaches a water stream and it doesn't degrade and it floats. And what happens is it floats in the oceans, and because the Earth is round, all of the currents meet somewhere. And so there are 2 major places in the Pacific where currents meet. And in past time, you could find there wood, all sorts of things like that. Now, you find the 2 big garbage patch. What are they? They are 2 islands, north and south, just made of plastic. Do you know how big they are? If you're European, they're as big as France. If you are Asian, they're as big as the Philippines. The only problem, they're growing. They're going to be bigger than France and the Philippines. And sometimes I read in the news, a rich person here and there, because they're rich, they send 3 boats to get the plastic out of a garbage patch. Think about it. 3 boats have to take all of the Philippines worth of plastic. Huh? That's the PR we live in this world. Huh? But we are creating these islands, and those islands are destroying life, and they're only growing. That's when it gets released. What happens when it actually goes in the environment? It becomes microplastic. Microplastic is something that goes into plants or plankton. Animals eat plankton or plants. We eat animals, or we eat salad, and we eat microplastic. And one can say, what does it matter? You eat 50 milligrams of plastic a week. If you live in Delhi or in Milan, you're going to breathe so much, that's nothing. Maybe, but a plankton that is just 1 cellulose big, once it starts eating plastic, tell me it's not genetically modified. And you say, let's not release plastic on the environment. It's not so simple. Why? Cars work on tires, Goodyear's invention. For a car to move, you need friction. That means that the relative velocity at the point of contact between the tire and the ground is 0, static friction. For static friction to exist, materials must wear. And so every time a car moves, you're releasing microplastic. And all of his talk about, let's go electric. We've solved the problem with electric car. Electric cars are heavier. They release more microplastic. Okay, let me walk. Look at your shoes. They are consumed. Whatever is not on your shoes is in the environment. And the numbers are enormous. Only from cars is 7,000 tons a year, only in Switzerland. Switzerland is a neighborhood of Chennai, just to be clear. Switzerland is 1/3 of Chennai at 7 million tons, 7,000 tons. All of Europe is 400,000 tons. The United States, which they drive more, is 500,000 tons a year. 5 million tons in 10 years. These are the problems we have. So, now I'm going to say something unpopular versus some of my colleagues. Some of my chemist colleagues will say, let me do research. I'm going to make plastic recyclable. You're like, well, good. Do you know how much recyclable plastic we have right now around? 75%. 3/4 of our plastic is already recyclable. We just don't recycle it. So you're going to make plastic recyclable? Sure. You're going to work on the left 25%. But we're still doing this. Why? Well, the reasons are multiple. The number one reason, virgin plastic is way too cheap. New plastic is way too cheap. You can publish how many science papers you want on new recycling things and convince Tata Steels to recycle plastic. It's still going to be more expensive than virgin plastic. Even if we went to go at zero chemistry approach, you still have to collect it and separate it. And so the second thing is our recycled plastic is less good than the new one. That's another big problem. And then, let's face it, there are entire countries that have no plastic recycling facility at all. And they are developing countries, okay, but they're not so poor country. Vietnam and the Philippines, there is none of these two countries, there is a single plastic recycling facility. So, only thing you can do there is to throw it in the water. Or burn it, if you are disciplined. Now, what are the solutions we are looking at right now? You can depolymerize to monomer and remake a plastic that's identical to the previous one. That's a good solution. The problem of that is it's still going to be more expensive than the original one because you need to collect, separate, depolymerize, purify, repolymerize. Second, upcycling. Let's depolymerize this time to something we can use to make something that costs more. This is something very good if it were to exist, because then you can say to Vietnam, take your plastic and make it into a conductive polymer and sell it at double the price. Now you have an economical incentive. We need to think that way. But we have no chemistry for that. You are the future, okay? Third, let's use biosourced, biodegradable polymer. Plastic that comes from Earth returns to Earth. The problem of this is, coming from Earth, it doesn't come from free. If you grow plants to make plastic, they're not making food. Also, if all of the 40 million tons of plastic we were producing now were to be made of a magical material, cellulose, okay, coming from trees, and maybe the trees are making coconuts, so we're also eating. Now you would be degrading a sugar at 40 million tons a year on Earth. You will change the whole ecosystem of the world because the bacteria that degrade cellulose would win over all other bacteria. When will humans stop thinking that we can mess around with nature and no consequence? So that's a difficult problem, a really difficult problem to solve. And importantly, we miss a recycle by design approach. What is that? Now I'm going to tell you a little bit my thinking. What I told you all the way to this slide, these are hard numbers, okay? These are hard numbers. You have to look at them and realistically address the problem. Now I'll tell you my thing. When I looked at this number, I was desperate, really desperate. And I said, you know, only thing I can do is look at nature, and let me try to learn from nature. What do I learn from nature? Recycle by design. What is that? Nature is made of, all living things are fundamentally made of polymers. They can be sugar-based polymer, cellulose or lignin, and proteins. These are the two things. They are sustainable. There's no accumulation of natural plastics. But what you notice from nature is something. Nature has time of synthesis, time of use, time of degradation that are roughly the same. Let me convey this to you. Not here that you don't have many seasons, but in places where you have seasons, on a tree, a leaf grows in a season, is in use in a season, and degrades in one season. Wood grows in a certain amount of time, stays in use roughly the same amount of time, and degrades the same amount of time. And in fact, wood degrades at different speed, but that depends on how long the tree was alive for. Human being, before modern medicine, our expected lifetime was around 50 years. So that's about 20 years for growing bones, you know that, 20 years in use, and if you throw bones in the environment, it takes about 20 years to degrade. You see, nature does that. So if we want to do plastic, we have to learn that. The time of use and time of degradation have to match, otherwise we have accumulation. But I had the pleasure of drinking some water from a glass bottle. That glass bottle got a use total maybe of a week. How is that possible, right? How do we do that? And so I thought, Francesco, you're still screwed here because, but then I thought, how is a butterfly sustainable? Butterfly lives about a couple of weeks, like the water bottle. When I posed my question to this, I thought that butterflies live one day, but it's not true. It's a stereotype. There's only one butterfly on Earth that lives one day. 2 weeks, more or less. So pose yourself this question. How is a butterfly actually sustainable? It lives only 2 weeks, and it won't degrade in 2 weeks. Why don't we find butterfly waste all over? Let me tell you why. Here I'm going to contaminate fields. One other hat that I used to have at EPFL is director of a food and nutrition center. Butterflies are sustainable because proteins on Earth are mostly recycled through their metabolism. Every living being eats. When we eat, you've eaten breakfast, not me, but you have this morning. What you've done, you've eaten a random mixture of proteins. None of you knows which protein you ate, correct? What is happening in your body, enzymes are chopping those proteins into amino acid. And then in your cell, the ribosome takes the information from the DNA and produces the protein you need in that moment. So if you ate a salad this morning, right now what's happening in your brain is that your cell is taking the proteins from the salad, putting them back together and making a neuron that helps you think. What I say is for most people, this is a wonderful example of upcycling. Not for everybody, but for most people. So what you need to understand is nature gives us the ideal recycling approach. You take a mixture, you don't need to separate. You get the amino acid, and then you produce something that is as good as new. My brain is not make or recycled proteins. It's my brain, correct? This is how nature recycles protein. So just to repeat, nature takes a protein, which is a sequence-defined polymer, where the sequence is a sequence of amino acid. And the amino acid determine the shape and the function of that protein. But when that protein is eaten, enzymes chop it, the ribosome rearranges it and polymerizes it in a new protein. So in nature, an animal that's eating silk can produce wool. An animal eating wool can produce silk. You understand that? And that's my idea of a future of recycling. And this is what I call NaCRe, something where I can take a random mixture of sequence-defined polymer, chop them, and then have a way of putting them together in something else. And then maybe taking that, a mixture of others, and starting again, and again, and again. And if you do this with proteins, the beauty is either you recycle and you produce upcycle, you produce something of higher value, so for countries where this is important, or if you release it in the environment, animals will eat it and upcycle it in the natural way. That's my dream for the future. So I had this dream, and I called this young student, Simone Giaveri, who's a material scientist who was working on paints in his master, and I tell him this idea. And he was crazy enough to say, let me try it. Let's do it in the lab. So now I'm going to go a bit technical. We took 3 proteins. We cleave them enzymatically, and we got the amino acid, and then we used the amino acid to make new proteins. Does it work? First protein is manganine. This is a mass spec of a type that Professor Pradeep showed you. And this is the mass spec of a digested protein. In gray, you see the theoretical amount of amino acid that you should have gotten, and in red, our experimental one. Then we take glucagon, we do the same. Then we take somastotin, we do the same. Then we put them together in pure, which is a mixture of a ribosome and all of the cofactors that allow the ribosome to work. And we get M-scarlet I, a fluorescent protein used for labeling in biology. Or if we just change the signal we give, we get GFP, green fluorescent protein. We can digest all 3 proteins together and get GFP. Now, these are sequence-defined polymers, and it took us a little time to actually understand them. So, for example, the yield was different depending on the protein, but because the yield depends on the limiting amino acid. So it's a different way of defining polymerization. But we didn't stop there. So far, I've taken 3 random proteins, cheap proteins you buy from Aldrich. But let me tell you what else we did. I called my friend, Raffaele Mezzenga. Let me introduce you to Raffaele Mezzenga. Raffaele Mezzenga is a person that cares a lot about sustainability. I hope I'm not going to make Professor Pradeep mad now. Huh? He makes water filters. In India, with a company called Blue Act. What do they do? They take beta-lactoglobulin. What is it? It's waste protein from cheese production. Just that. It's what is wasted from the yogurt you eat in the morning or during the day. And he takes this and makes water filters. And they are fantastic water filters, not to be used in big installation like Professor Pradeep, but at home. The beauty is they are made from food waste. But I told him, Raffaele, but the end of life of this, what is it? He goes, I don't know, because that's how we think. Give it to me. Let me show you that I can make something more valuable at the end of life of this thing, so that people will give it back to you, and we can reuse them. So we took beta-lactoglobulin, films made for water filtration, and we transform it in green fluorescent proteins. Then I went to another friend of mine, Fiorenzo Menetto, who uses silk to make electronic devices. Again, what's the end of life? Give it to me, and we transformed silk. Now, we can do this in multiple cycles. That means that I can actually take what I have, what I've produced, take the green fluorescent protein, take M-scarlet that was derived from a mixture of silk, beta-lactoglobulin, and various other proteins. I make green fluorescent protein. Then I take that, I digest that, and I make M-scarlet out of it. You see, you can keep doing it. In this way, you don't tax Earth, you keep reusing things. And your starting material can be something as nice as food waste. Do we need to make green fluorescent proteins? No. if, for example, the chemical industry has need, I can make enzymes and sell them at a high price. This is an enzyme that does the reaction there, which we made. You see, this is an enzyme that catalyzes a reaction made from food waste. That's how nature works. We are used to that, but our industry, our thinking is not used to that. It's not used to this continuous gaining. So now you could tell me, okay, but how much food waste is there? And this is true that I can use food waste as a starting material. Again, let me show you an example from the work of Raffaele Mezzenga. He was contacted by a local Swiss industry that produces tofu. Now, to make 1 ton of tofu, you produce 3 tons of waste. And he got that waste, the waste from tofu production. It's protein rich. He extracted the protein, and from that, what you can see in the right image there, produced 1 kilometer of packaging material for bread for another local industry. From tofu waste to bread packaging. That's the way we have to think in the future. And the reason I'm here to give you specifically this talk is because this is that field that is starting, okay? A classical chemist will think in a purist way. I need a very well-defined starting material. No, we need to use what we have from nature, live in equilibrium with nature, and use that to produce materials. And if you believe in what I said, you can use my method to, at the end of life, recycle and sell it at a higher price. This way, you have an economical purpose to doing it. Now, a little bit of science. What I told you is a sequence-defined polymer can be recycled in something else. But I've shown this only for proteins. Let me show this to you for DNA, which is another sequence-defined polymer. It works the same way. You need to chop DNA into the 4 bases. This is very easily done. It's an hydrolysis. But what you form is monophosphate bases, and what polymerizes is 3-phosphates. You have enzyme that generate the 3-phosphate, and then you use PCR to actually produce DNA. And so in this paper, we showed we could produce DNA, and here what you see is we took calf DNA, again, cheap DNA that comes from a side product of meat production. And we chopped it, changed it, and made it in plasmid DNA to produce GFP. Right? Something very important in the biotechnology industry, and that's the GFP we produced. With DNA coming from calf, very cheap, common DNA. And once we did that, we saw that we were very good, and our bases that we were producing like this were good to do PCR. So we said, so many PCR kits have been used during the COVID pandemics, and that's a lot of waste and energy. Can we recycle them? And so what you need to do is to make a primer that doesn't digest. We modified it, and we made recycled kits that could be digested. And this is the result. So I'm going to conclude here, just saying that plastic is a difficult problem. There's no silver bullet solution. And let me add to this. It's not just plastic. We consume 50 kilograms of plastic a year, but we consume 5 kilograms of copper, 15 kilograms of steel, 7 kilograms of aluminum. Here there is an expert of cement that will tell you how much cement we consume, who is a Farook College alumni, huh? But also alumni of my own university. So all of these things are enormous numbers. If we don't learn to live in equilibrium with nature, we're going to destroy nature. And for each thing, we need to think circular, but don't look just at the poster thing. Think it through, because the problem is complex. My dream is shoes and tires that are made of proteins, so that we don't pollute Earth. But for that, a lot of people have to work on this. Let me conclude thanking my group. I've shown the work of 2 people, Simone Giaveri, who's now a postdoc in the metabolism Max Planck in Marburg, and Wayne Aliu, who's finishing postdoc with me. I need to thank my funding agency. This work was funded by Europe's most prestigious funding, which is the ERC. And I need to thank you for your attention. I left ample time for student question, huh? But Pradeep first.
We'll be waiting for your questions, dear students. Make use of this opportunity.
Very important that students ask questions, and so now that I raised the question, hand, let me ask the question first. Fantastic thought, and that's the way forward. You are showing that proteins can be made, many others can also be made, and the whole world can be following this route. Fabulous. I wanted to ask you whether you have looked at the overall sustainability of this process. On the one side, proteins, polymers can be converted to new polymers and new materials. Proteins can be made to new proteins, etc. But lots of new materials, catalysts, reagents, all of them would have gone into it, energy would have gone into it. If you look at the overall life cycle, is that sustainable? I wanted your thoughts on that.
Pradeep, it's a question. So some people are looking at it in a big project that we have in Switzerland, people that do this type of sustainability. The real problem is, so the starting material you get from food waste, so it's negative carbon footprint because it would end up being burned. The energy after, I have numbers, but on a lab scale. Nobody has industrialized this process. So the only thing I can say is right now, menthol, a very simple molecule, as you know, it's cheaper for Novozyme to do it enzymatically than for BASF to do it chemically. So we are in this era where this enzymatic thing can be scaled up. Will this be scaled up? I don't know. Also, I've done many things in my life. What I'm not is a chemical engineer. So I don't know. The process is, in my cheap answer to you is, nature does it. We should be able to do it. So let's do one professor, one student. So if you don't ask a question, Sebastian cannot ask a question. That's not going to be fair, right?
Chocolate is ready here. If you want punnakai, I have one.
There is a question. There is a question.
There is behind.
Sir, I have one simple question. So if we repolymerize this mixture of amino acids, we will get a mixture of new proteins, right? So is this a selective process?
Super selective. The ribosome polymerizes only the protein for which you put the plasmid DNA in. It produces only one product. Only one. It's super, super selective. Which also means, in sequence-defined things, that you're going to have amino acid left, which you have to think to reuse, right? But it's a super selective process. One product, super pure. Sebastian now.
Okay, nice talk. I just want to connect to three technologies here. So one is the plastic removal. If plastic can be used for the energy production by gasification, so I think coming around 2 to 3 megawatt of energy can be produced from ton of plastic. Then CO2, you already mentioned that one. The CO2 can captured and utilize it actually. So chemical engineering come into the picture.
So I totally agree with you, and that's why I said there's not one solution. This is one thing that should be done, and it's a future of major simple plastic like the ones for the chairs, right? But with that, you have not solved the problem of the tires, of the shoes, of everything.
Absolutely, absolutely.
Yeah, you see? So we need to go, that's why I say it's not single bullet, right?
True.
And none of us should sell what we do as this is the solution, right? So there will still be polystyrene and polyethylene 100 years from now. They are too cheap and too simple, but they need to be recycled this way. But here comes society. This cycle will produce more expensive plastic than what comes from fossil fuel. And politics have to tax this so the two prices are the same. Otherwise, we are screwed.
No, I'm just bringing to that point. So in that case, we have to do the life cycle analysis,
See.
right? Okay.
Yeah, so can I ask one question here on behalf of students?
Okay, very good.
Not
Then
my question, on behalf of students. The students would like to know the polymers, natural polymers are biodegradable. And synthetic polymers are not biodegradable, most of them, right? And then if you're able to cut, natural polymers using your tiny scissors, why can't we do that in the case of man-made polymers?
super good question, super good question. There is a line of research on that, generating bacteria, for example, that can digest polyethylene. My problem with that is these bacteria are very minor bacteria on Earth. If we start spreading them, they're going to multiply like crazy because there's tons and tons of polyethylene to eat. And no, on top, what we don't do, okay, humans now have learned to do life cycle analysis. What does it mean? Analysis of the money. We don't do the analysis, ecosystem analysis, right? The problem of spreading this bacteria is going to mess up the ecosystem. And what's the consequence of that? You are the teacher of the future. You need to think, it's not just market and money. It's Earth. We need to leave Earth at least as good as we found it to our kids. And there's an ecosystem analysis to be done.
Thank you, that's very interesting. The students should know that.
Thank you, Professor Stellacci, for your inspiring talk. We have a beautiful moment to be given as a token of love from the conference organizing committee.